Hey everyone. So at this point, we know kind of the basics of electricity and we know how to relate voltage, current, and resistance to each other. So we're getting really, really close to building our first circuit. But right now, I want us to talk quickly about resistance again, because up until this point, we've really just talked about resistance as how easy it is for electricity to flow through a wire. And I mentioned at one point that different wires might make it easier or harder for electricity to flow. Copper is really nice, but like a tin alloy, not so much. But there is something else that we often use to add resistance intentionally to a circuit. And the reason that we might want to do that is to direct the current where we want it to go. So if we make it really easy for it to go in one direction or really hard to go in another direction, we can determine how much current is going to go in which direction. And we're going to talk about that when we study Kirchhoff's laws. But today, what we're going to talk about are some devices that we call resistors. And I've got a picture here. These are all different sorts of resistors. Most of these are fairly outdated. Most resistors that you see today are going to look sort of like this one. But a resistor is essentially ceramic, so clay, that has a certain amount of additives included in it so that only a very controllable amount of electricity can go through it. And so what we do is we actually have a color code. And so you'll notice like these different colored bands. Well, we can use a color code to tell us how many ohms of resistance each of these is providing. Um, Now, when we're thinking about resistors, so we talked about current earlier, we talked about water down a like hill, right? And that's one of my favorite analogies for um, dealing with electricity. But if I'm dealing with resistors specifically, I like to think of each resistor as kind of a stoplight. And it is going to hold up traffic for some amount of time. So obviously, some of these are going to hold up traffic a lot more than others, but that's kind of how I like to think about resistors when we're planning them. And so each resistor has a specific resistance. So like 100 ohms or 2000 ohms. And one of the things that is really important to us when we're doing circuit analysis is to think about how sets of resistors in different arrangements will result in a different overall resistance for the circuit. All right. So if we think of, and you already did some of these problems with Ohm's law, right? If we have a circuit with a voltage on the battery of 18 volts and a resistance of 6 ohms, we can calculate using Ohm's law the total current coming out of the battery. And so we'd say 18 equals 6I, and I will be 3 amps. But what if we had more than one resistor? So what if we had a circuit that looked like this? Or a circuit that looks like this. So in each of these cases, we have more than one resistor. Does that mean that each of these is going to behave the same way? Turns out no. So let's talk about those two ways of arranging things. We call this series. We call this parallel. And a key difference between these two is that, as you can see, in series, let's think about these electrons that are coming out of this battery. Every single electron that comes out of that battery has to go through the first resistor, the second resistor, and the third resistor before it can come back into the battery. So if we're using our stoplight analogy, it's like everybody leaving work is going through the same way home, and they have to stop through the first and second and third stoplights, every single one of them. Over in parallel land, things are a little different. Here, when electrons come out of the battery, they have a choice to make. Do they want to go to the top? Do they want to go to the middle? Do they want to go to the bottom? They can't do all three. They can only do one. So again, if we want to return to our stoplight analogy, then it turns out that this is like everybody's leaving work and there are three different ways home. Now, whichever way you go, you're still going to have a stoplight, but you only have one stoplight. And that is really inherent to the difference between these setups when we start thinking about equivalent resistance. So equivalent resistance is, hey, I've got this grouping of resistors and I want to replace them with one resistor, but end up having like the same current, same voltage, everything else the same. What resistor would I change it with? Now, this is something we do in lab, in class. We actually hook up like a 6 ohm resistor and then two 6 ohm resistors and then three 6 ohm resistors and 4 and 5. And what we end up finding is that for every resistor you add, so number of resistors, total resistance, for every resistor you add, you basically just add that much resistance to the circuit. So in this case, if we want to look at like a more generic way of writing that, we would say that the equivalent resistance is the first plus the second plus the third plus however many others we have. So in this particular example, it would be 6 plus 6 plus 6 or 18 ohms. So we've increased the resistance by putting them in series. Why? Just like with the stoplights. If you have stoplight after stoplight after stoplight, it's going to take you longer to get home. Now, over here in parallel, this is where people get a little weirded out because it turns out that if we do that same lab, but we're putting them in parallel. So one resistor would just have like a resistance of 6. But if we put in a second resistor, we get a resistance of 3 and then 2. And it goes down. And it actually ends up being an inverse function. And the way we write this in physics is that 1 over the total resistance is 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Now, if this means, so if all of the resistors are the same, this ends up being like 1 over the equivalent resistance is 1 over is whatever that resistance is, however many times you have it, n number of times. So that would mean that the total resistance would just be that resistor of one of them divided by how many of them there are. So this is kind of the opposite of what people think, right? We're adding more stoplights. How are we not making it harder? How are we making it easier? But the key is not that you are adding more stoplights, it's that you are adding more paths. So there's going to be less back of electrons, and the electrons are going to find it easier to find a route home because that route will only ever have one resistor in it. And it will have less of the current backing up at that resistor because it has multiple paths and the electrons are being spread multiple ways. This is something that we will use in class to do some circuit analysis problems with as well. And so we are going to turn some fairly complex circuits into just series and parallel portions. All right. Thank you so much. Have a great day.